Hi everyone, it's Mr. Corvin. I'm going to be talking to you in this video about Chapter 7.8, Improper Integrals. We're going to go through the examples in the textbook, then we're going to do one additional example, and that will teach you all you need to know about improper integrals. So first off, we need to talk about what an improper integral is. So we're going to extend the concept of a definite integral to the case where instead of just looking at a finite interval from a to b, we're also going to look at what happens when one or both of the limits is infinite. Either we're going from a number to positive infinity, we're going from negative infinity to a number, or we're going from negative infinity to positive infinity. Can we integrate in those situations? Also, we talked about that one of the conditions for integration is that an integral has to be continuous for the most part. We can have a few discontinuities in there. But what happens if f, the function that we're integrating, has an infinite discontinuity on the interval where we're integrating? All right, so in both those cases, we call the integral an improper integral. And kind of like an improper fraction, there's nothing actually improper about it. We just need to handle it with some extra care. So we're going to start by talking about type 1 improper integrals. So these are the more common type, and these are the ones that have an interval that involves infinity some way. One or both of the limits are infinite. So we're going to consider, for our first example, we're going to look at the region S. It's an infinite region. It lies under the curve y equals 1 over x squared. It's above the x-axis, and to the right of the line x equals 1. Okay, so you can see down here, there it is. This is the area that we're talking about. So here's the curve, y equals 1 over x squared. Here's x equals 1, here's the x-axis, and that's the area that we're referring to. Now, just because the interval is infinite does not mean that the integral is infinite, that the evaluation of the area is infinite. So that's what we're going to see here. So we're going to just do what we normally do and evaluate the integral as best we can. So we're going to say that the area is the integral from 1 to t. So we're doing this integral like an area function. So this was one of those things that you learned about in Calc 1 when we started to define an integral. We said, yes, this is part of the fundamental theorem of calculus. We can look at this as the area function. This is why we need to use that precise definition. So here's t. T is some arbitrary number that's bigger than 1. I have no idea why I just did that. But anyway, t is some arbitrary number that's bigger than 1. So we're going to, instead of finding the area from 1 to infinity, we're going to find the area from 1 to t. And we're going to find a formula for it. So a of t equals the integral from 1 to t, 1 over x squared dx. We know the antiderivative of 1 over x squared is negative 1 over x. And we're evaluating that from t to 1. Now they skipped a step here, so I'm going to put in that missing step. So this equals negative 1 over t minus negative 1 over 1. So that's negative 1 over t plus 1, which they rearranged as 1 minus 1 over t. And let's notice that this gives us a function in terms of t. So for any value of t, I can find the area as long as t is greater than or equal to 1. So that looks pretty good. So now what happens as t goes to infinity is the question. All right, so we know first off that a of t is always less than 1. We have 1 minus 1 over t. So t is a positive number, and so 1 over t is a positive number. So we're subtracting a positive number from 1. And this is the key right here, is that the limit as t goes to infinity of a of t. All right, so as t goes to infinity, the area gets closer and closer to 1. So the area of the shaded region approaches 1 as t goes to infinity. So we are going to define the area of the infinite region S to be equal to 1. All right, so this is the key right here. If we're doing the integral from 1 to infinity, or from any number to infinity of some function. Really, the strategy is we're going to replace infinity with some letter. They've used t here. And then we're going to take the limit as t goes to infinity. So that's the strategy here. Rather than just, because you can't plug in infinity, that doesn't work. So instead, we're going to introduce a new variable, and then we're going to use that variable and take the limit as it goes to infinity in order to determine what the in order to find the area. All right, so that example was a guide. Here's the definition. So we're going to define, this is for all improper integrals of type 1. So this covers the case where we have positive infinity, negative infinity, or both. So case A is when we just have positive infinity. If the integral from a to t of f of x dx exists for every number t greater than or equal to a, then we define the integral from a to infinity of f of x dx to be equal to the limit as t goes to infinity, integral from a to t f of x dx, provided that the limit exists as a finite number. If it goes infinite, then the area doesn't exist. So this is what we just saw. This is the same thing. And then similarly, I'm not going to read it, but similarly, if instead we're dealing with a negative infinity situation, we're going to replace the negative infinity with t, and we're going to take the limit as t goes to negative infinity, and do the same basic thing. All right, here's some important vocabulary right here. We're going to see these words a lot in the rest of the class. Okay, convergent versus divergent. If the improper integral exists, if the limit exists, we say that it's convergent. And if the limit does not exist, we say it's divergent. And in essentially every scenario where this is going on, if it doesn't exist, it's because it's going off to infinity or negative infinity. We're not dealing with, in general, I say in general, we're not dealing with some sort of weird oscillating back and forth situation. So anyway, but that can happen. Like, you can make anything happen if you make a function that's messed up enough. All right, but now here's the question. What if I'm going from negative infinity to infinity? Well, in this case, here's what we don't want to do. What we don't want to do is we don't want to just say, oh, limit as t goes to infinity, negative t to t, f of x dx. Can't do that. That is a big no-no, because what can happen in that situation is you can actually make that use functions where that exists, but the whole integral doesn't. So that's actually a big problem. So we don't want to do that. What we do in that case is we actually split the integral, and we can split the integral at any number a, according to this theorem. And once we do, we look at each of the pieces separately. So we have a type B integral here, and we have a type A integral here. We look at both of them and see if each of them exists, and if they both do, then we're good. We define the integral from negative infinity to infinity to be the sum of those two. 99% of the time when you have this situation, you're going to split at 0. Splitting at 0 is the easiest, but you don't have to. You can use any value of A that you want. Just be cautious. Don't try to shortcut it and just go from negative t to t, because I can make that not work. All right. We want to interpret this as an area if f is a positive function. If f is not a positive function, we can interpret it as the net signed area, but again, let's be careful here. We're going to focus mostly on positive functions. Okay, so here's our first example. We're going to determine whether the integral from 1 to infinity 1 over x dx is convergent or divergent. So this is the situation. So what we're going to do is we're going to start by replacing the infinity with t, and we're going to use limit as t goes to infinity. All right, so we're going to replace that, like I said, limit as t goes to infinity, integral from 1 to t, 1 over x dx. All right, we know the antiderivative of 1 over x is the natural log of the absolute value of x. And we're going to evaluate that from 1 to t. So that's the limit as t goes to infinity, natural log of t minus natural log of 1. And we know that natural log of 1 equals 0. Write that in there. All right, so that equals 0. So I'm left with the limit as t goes to infinity, natural log of t. And we know that that does not converge. As t goes to infinity, natural log of t just keeps increasing and increasing. So that goes to infinity. So this is a divergent integral. So we've determined that it is divergent. Okay. As there's the formal, write-up of the limit does not exist as a finite number, and so the improper integral of 1 to infinity 1 over x dx is divergent. Okay. So what we want to do is we want to say, well, wait a minute, we had two different functions. They were kind of similar. One converged, one diverged. What's the deal? Like, is there, a cutoff point? What's going on here? So when we saw with the first example we looked at was we saw the integral from 1 to infinity 1 over x squared dx, and then we saw the integral from 1 to infinity 1 over x dx. The first one converged, the second one diverged. Okay? They both look very similar. Like, you can see that 1 over x squared is decreasing significantly more rapidly. I mean, the question is, why is that decrease enough to give us a finite area, whereas the other one gives us an infinite area? And can we find a dividing line? Is what it comes down to. Pardon me. Excuse me. All right, so can we find a dividing line? Well, it turns out we can. It turns out the dividing line is 1. It's not, this is not too much of a surprise. You can power rule it. I mean, you can just say, oh, it's 1 over x to the p. Let's say that p isn't 1, and then we'll integrate, and then we'll go, oh, yeah, we can make this converge if p is greater than 1. All right. So this is the key summary of that. This is going to come back later in something called the p-series test. Okay, there's my pen. All right, so the integral from 1 to infinity of 1 over x to the p dx is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So that is a very key theorem that you need to know. Let's actually take a quick look and see why exactly that is. So I'm going to come back to this. Oh, no, that's not what I wanted to do. Go back. That's not what I want to do. Okay, I'm going to pause for a second. Okay, I think I got the thingy thing to work, but maybe not, because now it's going back to the thing. Screen. Show taskbar. Scooch that out of the way. There we go. All right. I hope it's still recording, because now I can't see what's actually happening, or if you can see what's going on. So let's actually see why that is. So we're going to look at the integral from 1 to infinity, 1 over x to the p dx. And we're going to assume that p is not equal to 1. Because if p is equal to 1, then we already examined that situation. So this is the, that's a whoopsie. Let's erase that. Oh, that's nice. So this is really the limit as t goes to infinity. 1 to t, x to the negative p dx. So the rule for integrating with power function is that you add 1 to the exponent and then you divide by the new exponent. So this is limit as t goes to infinity, x to the 1 minus p divided by 1 minus p, being evaluated from 1 to t. So this is the limit as t goes to infinity. t to the 1 minus p over 1 minus p minus 1 over 1 minus p. All right, so then the question is, as t goes to infinity, does this converge or diverge? Well, this part right here, it just always converges. So the question is, when does this converge? Well, it converges, since t is going to infinity, it converges if 1 minus p is less than 1. Or excuse me, if 1 minus p is less than 0. All right? Because it has to be less than 0. We have to have a negative exponent here, which basically just says that that p is greater than 1. Excuse me. So that's the generic proof of it, of what we just saw. Okay, so it says it recorded that, and hopefully it actually did. So we'll cross our fingers and then view the recording later and just hope that that actually worked. Okay, moving right along. There we go. Ha ha ha. Type 2, discontinuous integrants. Okay, so now we're going to look at the improper integrals of type 2. So we're supposing that f is a positive continuous function defined on a finite interval with a vertical asymptote at the endpoint. Now, we don't actually have to have the vertical asymptote at the endpoint. If it's in the middle, as you'll see, we'll just split it like we did before. But it's just easier for the purposes of defining it to say that the asymptote's at the endpoint. All right, so S is the unbounded region under the graph of f and above the x-axis between A and B. So the difference here between type 1 and type 2, in type 1, the region was extended indefinitely in a horizontal direction, so along the x-axis. Here the region is going infinite in a vertical direction, so parallel to the y-axis. All right, so here we have our lovely picture, and we see that t is a number that is greater than a, or greater than or equal to a, and less than b, and we want t to approach b. So again, we're setting up this area function. It's the integral from I to t of f of x dx, and we're going to take the limit as t goes to b. Here we do have to make a note of which side the discontinuity is on. If the discontinuity is on the top limit, then we look at the limit as t goes to b from the left. If it's on the left side, we take the limit as t goes to b from the right. Obviously, in that case, b would be in the denominator. And again, we don't have to have f be a positive function. Doesn't really matter what type of discontinuity it is. But this lets us define a type 2 improper integral. All right, so here we have similar definition to the one you already saw. This is for a type 2 integral. Again, we also see the phrases convergent and divergent. You know, there's a lot of technicalities in here, but it's the same basic idea. Except here, when we do the limit, we're not doing the limit as t goes to infinity or negative infinity. We're doing the limit as t goes to a finite number, either from the left or from the right, as appropriate. So let's take a look at an example of this. So we're going to find the integral from 2 to 5 of 1 over square root of x minus 2 dx. And key thing to note here is, where is there a problem? So the question is, why is this an improper integral? Where's the problem? And that's the thing about improper integrals. Sometimes they're sneaky. You're not told, hey, this is an improper integral. So you have to be vigilant for, like there could be a problem here. In this case, we see, hey, that's not defined at 2, but yet we're integrating from 2. So that's a big problem. So let's see how they handle that. And we see that so first off, they note, hey, here's why it's improper. And then we're going to do the limit as t goes to 2 from the right of t to 5 dx over root x minus 2. Excuse me. So the way they did this was they said, hey, x minus 2 is going to be root x minus 2 in the denominator is going to be x minus 2 to the negative 1/2. So we're going to add 1 and do that. So they did the integral, they skipped a couple steps, but now they're ready to plug in. So we have 2 times root 3 minus t minus 2. As t goes to 2, that second part is just 0. So the answer we get is 2 times the square root of 3. Okay, so we are interpreting it like this, and you can see from the picture here that the area is finite. A helpful tip, and it's not like 100%, but it's like pretty good. Helpful tip. If you're doing a type 1 improper integral, we know we have the p-test, you know, that if p is greater than 1, we're going to converge. When you have a type 2 improper integral with a function like this, you can also do the p-test, except now it's going to converge if p is less than 1. If p is exactly 1, it doesn't end up converging either way. But that's the basic idea behind it. Again, it doesn't work 100%, but it generally works. All right, so now we're going to talk about this important idea of a comparison test. So this is the first time we've brought up the comparison test, and the idea here is that we're not going to find the area of the function that we care about, but we're going to determine if it is a finite area or not. And this is really useful because basically this is a big time saver. It's like, hey, I'm not going to waste my time, you know, trying to do this integral and oh, it diverged. I'm going to check before and be able to say whether it converges or diverges. All right, so this theorem is going to come up again and again and again later in the course. So this is the comparison theorem for integrals. And we're going to talk about in terms of type 1 integrals. There's a similar way you can do it for type 2 integrals, but we actually don't really care about it so much for type 2 integrals. But for type 1 integrals, we're going to suppose that f and g are continuous functions. And we're going to say that f of x is greater than or equal to g of x, and that g of x is greater than or equal to 0. So we have non-negative functions. F is bigger than g. And we're going to assume that that's true after some point, A. It doesn't have to be true 100%. It just has to be true eventually. And so the theorem states, if the area under the higher function converges, then the area under the lower function converges. Similarly, if the area under the lower function diverges, then the area under the higher function has to diverge as well. That's what the comparison theorem says. And here's the picture of that. We're saying if the area underneath f is finite, then the area under G has to also be finite because it has to be less. If the area under G is infinite, then the area under F also has to be infinite because the area under F is more. That's the basic idea of the comparison theorem. Okay? Now, what if I have that situation and I know that the area under F is infinite? You can't say anything about G. What if I say, oh, the area under G is finite? You can't say anything about F. So it only works in that very specific situation. So as an example, we're going to show that this function is convergent. So this is an important example because we know that this function does not have an elementary antiderivative. We can't actually calculate this area using techniques that we know. We actually can calculate this area because this is a special function, but it doesn't have an elementary antiderivative. So we can't evaluate the integral directly. That's not an elementary function. Again, like, you know, hey, it's related to the normal distribution, so we kind of can. All right. So what we're going to do is we're going to look at, we're actually going to split this. And the reason we're going to split this is because we're going to look at another function to compare this to. And the problem is that from 0 to 1, the other function's higher. So this is a theme that's going to come up frequently. Or excuse me, the other function is lower. I mean to say, I need a higher function if I want it to converge. And so you see this a lot. You basically can go, oh, as long as it eventually works, you're fine. just throw out that part at the beginning that doesn't work. Just throw it out and focus on the part that does work. As long as it eventually works, then you're good. So that's what's happening here. We're saying it works after 1. So we're just going to look from 1 to 0. And I don't even know what that is, but I know that it's finite because it's a finite area. There's nothing improper about it. Just an ordinary integral. So we're going to just look from 1 to infinity. All right, so now we see here in this diagram. So we're going to compare e to the negative x squared. Where did my pen just go? There it is. We're going to compare e to the negative x squared to e to the negative x, which I do know how to integrate. And e to the negative x is clearly above e to the negative x squared as long as we're past this point right here when a equals 1. All right, so we see that right there. And they did a little proof of it. All right, we know how to evaluate the integral of e to the negative x. And we get that it's a finite value. So we do the improper integral. We get that it's a finite value. It's convergent. And my conclusion then is, by the comparison theorem, since the higher one converged, the lower one must also converge. Okay? So the integral from 1 to infinity e to the negative x squared dx is convergent. And therefore, since from 0 to 1 we're just adding on a little extra, it follows that the integral from 0 to infinity e to the negative x squared dx is convergent. And by symmetry, we could say that the integral from negative infinity to 0 e to the negative x squared is convergent. So therefore, the integral from negative infinity to infinity e to the negative x squared is convergent. So there's a lot of fun things you can do with that. But this comparison test is going to be really, really handy. It is kind of the underpinning of what we're going to do with sequences and series. All right. Do I want to keep my ink annotations? No, let's discard those. All right, but what I do want to do is I do want to go back to my sketch pad. I don't know how to use this yet. I'm just going to trash that. Okay, great. So we're going to look at this example. So we're going to look at the integral from negative infinity to 0, x e to the x dx. Because this, I wanted to go over one example that was a little bit trickier. So this is our example. And this is a type 1 integral. All right, so we're going to look at this as the limit as t goes to negative infinity. Integral from t to 0, x e to the x dx. Okay, so this is an integration by parts situation. So that's what makes this tricky, is that we have to do this with integration by parts. So I'm going to let u equal x, and I'm going to let dv equal e to the x dx. du equals dx, v equals e to the x dx. So this becomes uv, so x e to the x. Oh, and this is where I'm a bad person, because I forgot to write my limits. Let's be a better person. Limit as t goes to negative infinity. X e to the x evaluated from t to 0 minus integral from t to 0. And then this is just oh, dang it, that's wrong. I don't know why I wrote dx there. That doesn't belong there. V is just e to the x. I'm just going to blame it on jet lag and the time zone change. That's not right either. There we go. E to the x dx. Alright, there we go. At least I caught the mistake. Okay, great. And now this is the limit as t goes to negative infinity. X e to the x minus e to the x from t to 0. All right, so that wasn't too hard to actually do the integral. So now let's evaluate. So this is the limit as t goes to negative infinity. By the way, writing that limit every time is, yeah, really annoying. So that's 0 minus e to the 0 minus t e to the t minus e to the t. Okay, great. So let's get the basics out of the way. E to the 0 is 1, so this is negative 1 minus the limit as t goes to negative infinity, t e to the t minus, I'm going to, minus is, shoot, and let's do it that way. Let's erase that. All right, and then I'm gonna write the limit again, just so that I don't have to deal with minuses. It zeroes out anyway, but I'm just gonna be really, really, really pedantic here. So now this is plus. Sorry, minus is plus. E to the t. All right, so there we go. So the negative 1 came from here, and then the limit's applied to this, and then this is a plus because minus distributed. Okay. So this part right here, as t goes to negative infinity, we know that e to the negative infinity is 1 over e to the infinity, which is like e to the infinity is a really big number, so 1 over it's a really small number. So that goes to 0. The question is, what about this? Technically, we have to L'Hopital's rule this. So this is negative 1 minus the limit as t goes to negative infinity, t over e to the negative t. So now I'm going to L'Hopital's rule this. So that's 1 over negative e to the negative t. So this is now negative 1 plus the limit as t goes to negative infinity, e to the t, which again goes to 0, and so I get negative 1 as my answer. So this integral, oops, that wasn't what I meant to do. Undo. So this integral converges to negative 1. All right. So hopefully that helped you out in terms of understanding the 2 different types of improper integrals and what you need to do to solve each of them. And so please feel free to email me if you have any questions about that or about any of the web assigned homework or anything of that nature. All right, and so thanks for watching, and I will see you soon.